In this lesson, and to some extent the next, I'm going to talk about independence of path with regard to contour integrals. Under certain conditions, we can evaluate a contour integral by just taking the difference of the antiderivative evaluated at the two endpoints. And that's what we have in this theorem here, 125. If f of z is continuous in a domain, remember a domain is an open connected set D, and has antiderivative capital F of z for all z and d, then for any contour gamma contained in D with initial point z sub 1 and terminal point z sub 2, the following is true. So the contour integral about gamma of f of z equals the antiderivative evaluated at z sub 2 minus the antiderivative evaluated at z sub 1. Now I'm not going to provide a proof here, but if you're interested in a proof, you can look at Theorem 6 from section 4.3 in the book by Saff and Snyder. So the above theorem doesn't apply in all cases. We saw in the last lesson that f of z equals the conjugate of z squared is not analytic. You can verify that through the Cauchy-Riemann equations. But since it's not analytic, this theorem doesn't apply. And if you recall, we had a triangular shaped contour, and we needed to parameterize that contour and then evaluate the integral over each of the smooth arcs making up the contour. So it was rather complicated, but there was no way around that because we didn't have an analytic function. Now, on the other hand, and also in the previous lesson, we did evaluate f of z equals z around the contour, and that turned out to be path independent. We didn't have this theorem at that point, but we could have, now that we have this theorem, we could have used that, we could use that here to also evaluate f of z equals z around a given contour. If gamma is a simple closed contour, basically a loop within the demanded definition of a continuous function f, which has any derivative capital F for all points in the domain, then it follows from Theorem 125 that the contour integral about gamma of f of z equals 0. And the reason is when you evaluate your antiderivative of f of z sub 1 minus f of z sub 2, z sub 1 equals z sub 2 because the endpoints coincide when you have a loop. Now, we also have a theorem related to this that states that if you have a continuous function f in a domain, an open connected set, then these three conditions are equivalent. We already saw from up here that the first condition, f has an antiderivative, means that Theorem 125 applies, in which case we have this identity here that the contour integral over f of z equals 0 for every loop within the every closed loop within the domain of D. And this second condition implies the third. You can see that if you have two contours that have the same endpoints, you're basically forming a loop. And so if you take this contour about gamma sub 1 and you subtract this, gamma sub 2, you remember when you do a negative of a contour, that basically changes the direction. So effectively what you're creating between gamma sub 1 and gamma sub 2 is a loop. And that would give you integral 0, and then you just can equate these two from that fact. So going in this direction is kind of easy. What's difficult is proving that either one of these two imply that f has an antiderivative. And I'm not going to prove that here, but I'll refer you again to the book by Saff and Snyder. They have a proof for this. Okay, we have an example here of our Theorem 125 from the first slide of this lesson. So we have the function f of z equals sine z, and the antiderivative is minus cosine c. Is recall that when you take the derivative of cosine z, you get minus sine z, so we need a minus here. And it's fairly simple. The contour is what we've shown here, which is not so simple, but the evaluation is simple. So we have a sort of a straight line going from -2 to the point -1 plus I, then down to 0, and then a semicircle here. And all we need to know is the two endpoints in order to evaluate this. So we evaluate the cosine minus cosine z at this endpoint 2, and then we subtract, so minus and minus, cosine at -2, and we get our result. As a second example, we're going to take the integral of f of z equals 1 over z over this contour shown here on the right. It goes from the point square root of 2 over 2 minus I square root of 2 over 2, which is basically at an angle minus pi over 4 from the real axis, going to the point minus the square root of 2 over 2 minus I, the square root of 2 over 2. And this point is at an angle 5 pi over 4 from the real axis. We know from a previous lesson that the derivative of log z is 1 over z, so we have our antiderivative. The problem is that the log, as we defined it, we had a discontinuity along the negative real axis, and so our antiderivative doesn't exist, isn't continuous, I should say, along the contour that we've drawn here. So what we can do to fix that is we can move the ray of discontinuity to the negative imaginary axis, and that's what I've done here. I've redefined log z equals the natural log of the modulus of z plus I argument of z, and I've defined the argument of z going from minus pi over 2 to 3 pi over 2. And so the discontinuity is here now, and it doesn't affect our contour. So we can create an arbitrary domain. Let me just give you an example. The exact shape isn't important, but we can create an arbitrary domain, say, that looks, let me just make it squiggly just to make my point here. So the interior of this domain contains the contour and both our function and our antiderivative are continuous and analytic in this domain here. So we can use theorem 125 in that case. So we can now complete our derivation or evaluation of the integral of 1 over z, remembering our definition for the log as we redefined it on the previous slide. So we plug in the two endpoints here, the minus square root of 2 over 2 minus I square root of 2 over 2, and we have to plug that in for z here and here. And then with the other endpoint, we plug in also. So the two natural logs that we have cancel each other out. I've written those down here. You notice when you take the modulus of this one here, it's the square root of, minus the square root of 2 over 2 squared, which is 1/2. And then this is also 1/2. So you get the square root of 1/2 plus 1/2, the square root of 1. And you get the same thing here. And I've just written that out. So you get 0. So this cancels that. And then you're just left with the two arguments. And this one here is 5/4 pi I, the argument of this point. And the argument of the other point is a minus pi over 4. So when you subtract them, you get 3 pi over 2i. And that's our answer.